Another example, which is really spectacular, is that of kinesin. And kinesin is a walker, as I already mentioned. It walks on microtubules, mostly to transport matter from one spot in the cell to another spot where it is needed. A very beautiful video, which you can easily find on the web. This is that of ATP synthase. I should say that it's not science fiction. It is based on very precise scientific data. So ATP synthase is located on a membrane in the mitochondria. And there is this part at the bottom which spins. There is an axis here which is threaded in the hollow part of the big cluster of proteins, red and green here. And as it spins, ATP is synthesized from ADP and inorganic phosphate. It is very slow on the slide, but if you look at the real system, the real stuff, it spins very, very fast, a few thousand times per minute. Now, we will change completely topic and talk about catenanes and rhotaxanes. Catenanes are interlocking rings, and the 2-catenane, which is drawn here, is the simplest member of the family because it consists of 2 interlocking rings. So 2 holds for the 2 rings which are interlocking with one another. Rhotaxanes are somewhat similar. A rhotaxane consists, or the simplest rhotaxane, consists of a ring threaded by an axis, and at the 2 ends of the axis, we will attach big stoppers to prevent the system from dissociating. Why are catenanes and rhotaxanes so exciting in relation to molecular machines and molecular motors? Very simple. If you take a very simple rhotaxane, like the one here on the left, if you are able to move the ring from the left position here to this position on the right and go back to the left, you are very close to making a linear motor, very similar to a piston moving in a cylinder. And this, of course, will lead to a very simple molecular machine. But nobody had done that before the work of the various people working in this field of molecular machines. Similarly, if you have a rhotaxane of this type, and if you can rotate the ring around the axis, or here, rotate the red ring within the blue ring, which is considered as fixed, you are on your way towards rotary motors. So you can pirouette or you can even rotate. So this is why catenanes and rhotaxanes are so interesting in relation to molecular machines. And basically, catenanes and rhotaxanes led to this new field of molecular machines. Now let's try to make catenanes and rhotaxanes. Not so simple. Chemists have been talking about catenanes and rhotaxanes for more than a century. So this is a very old concept. But experimentally, the development of this field has been very, very limited. And I just would like to refer to some historical work done by Professor Schill in Freiburg in Germany. It's a neighbor city, very, very close to Strasbourg, my own city. And in 1964, so already many years ago, Schill and Lüttinghaus published a beautiful piece of work on the synthesis of a catenane. So that was the first time that a catenane was made convincingly. It was a great publication, very, very elegant. But the problem, or the weak point, let's say, was that it was a 22-step synthesis, so exceedingly difficult, and the overall yield was very, very small, very tiny. So chemists were really very impressed by the work, but nobody really invested work and time in this field because it seemed to be so difficult to make such molecules that everybody was kind of discouraged. So something new had to happen. And I will show you how we started in this field. So when I started my group, after working mostly with Jean-Marie Lane, my boss, I was very much interested in photochemistry, and in particular, there was a big project. Many groups were working on this project, which was trying to split the water molecule to H2 and O2. A big project, of course, very, very ambitious, because it's a dream reaction. And at the time, there was a hero in the 70s, in the 80s, in the 90s. It is still kind of the hero in the field. This is ruthenium trisbipyridine. Just to remind you, in the Mendeleev classification, ruthenium is just below iron. Ruthenium is a noble metal, which means that it is very, very expensive. And our project was trying to replace ruthenium by another metal, much, much cheaper. And so we embarked in a project aiming at using copper instead of ruthenium to make very interesting molecules in relation to photochemistry and electron transport.